it's good.
Very cool. Okay. Okay, so thank you, Moshe, for the opportunity. And this topic is about personal rapid transit systems. And this study was conducted here at the Afeka, together with my partners, Professor Ariel Avineri, Professor Yuval Cohen, and engineer Yaron Karib, who actually received his master's degree here at Afeka. So I think the problem is all very familiar to all of us. Big traffic jams all over the world. Actually, 2 days ago, some of my students were late for the class because of a tremendous traffic jam taking place at in Tel Aviv. And the question is, can we do something about it? So one approach is the PRT. PRT is a personal car, probably electric vehicle that comes by demand, under demand. It carries maybe 1 or 2 passengers. And it's not a new idea, probably known since the 1970s. And there are already 3 or 4 commercial demonstrations all over the world, successful demonstrations. And the idea is that you can get from anywhere to anywhere within your town, from a station to a station. If everything is connected or interconnected, you can get anywhere, and you don't have to stay in the jam, and you don't have to look for a parking lot, etc., etc. That's very, this could be very, very pleasant, actually. So what we are interested here in our research is we were interested in the energy supply thing, the energy management thing here. There are a lot of issues here, but we were focused on the energy supply because this is an interesting problem and valuable as it is. And there are a few options here. There's the battery, like any electric vehicle. And there are the other options of electric rails, like overhead catenary, which it's very, very common. Also the third rail, whereby people put another rail next to the driving rails to provide the electricity to the vehicle, to the train, probably. And there is the magnetic levitation, but this magnetic levitation is rather new technology. It's not yet well proven, no big commercial demonstrations, and also not a lot of data to work with. So we decided to focus on 2 options, battery or third rail. Overhead is a good one, but in very dense cities, when the streets are narrow and there is not too much space for this infrastructure, overhead will be problematic. So we are left with 2 options, which we consider attractive or generic, like third rail conductor and battery storage. So what is the objective? Is about developing a modeling and also implement it to the entire energy management system from the grid all the way through the battery and the powertrain and other elements to the wheels, and also taking into account balance of plant components such as the stations and other things that we will see later. There was a work, very big work or study that was made, what was published a few years ago about the attractive energy requirement without considering the entire system. So we decided to extend the model to include the whole system. It's actually what we do is actually to go from the wheels, from the tractive or propulsion requirement of the car through all the components to the grid. To get the whole picture about, to see the whole picture about how much energy indeed is consumed in this system, which is rather complex. So we picked a model. Our research is not about developing a new technology, okay? It's about modeling. So we picked up a vehicle model, which is a small car, electric car that that is suitable for PRT system rails, with small dimensions, can carry up to 2 passengers, and with some data considering the resistive forces of this car. This is how we. This is our vehicle. But vehicle is not enough. We have to consider the whole guideway system. So we choose for the case study the city of Herzliya, with 11 stations and overall rail length of something like 12 kilometers. And some other parameters which we have to consider is how many cars do we keep. Some of them are moving and some of them are idle. Some of the cars are occupied with passengers, others are empty. This was also considered in the study. This is actually a result. What we see here is a result of a previous study made by, again, a group of researchers from Afeka. That they were not interested in the energy problem, only in the infrastructure and the design. So this is the resulting data of their work. Now, we consider that the train or the pod car, the taxi, the car, whatever we call it, it's accelerating from the ground level, picking a passenger from station 1, say, and then cruising for the most of the distance, which is good from energetic point of view, because when cruising, the power requirement is minimized, and then braking to the other station. This is a typical network between 2 stations. And about the kinetics, this is rather standard mechanical physics. There are 5 forces acting on the vehicle. 4 of them are resistive: drag, rolling, gradient, and acceleration, if any. Of course, during the cruise, there is no acceleration, but in general, we have 5 forces. And the very important thing is what happens while braking. While braking, the car has energy, and the question is, can we generate electricity or energy while braking? Well, the answer is depending on our design. If we have a battery, for instance, then we can, because we can charge a battery. If we don't have a storage device, we probably cannot do regeneration without significant technical complications. So we also consider this effect in the study. So the kinematics is going pretty much as follows. You have the acceleration is changing. This is coming because this is a result of the comfort requirements from any vehicle. The vehicle can never drive under a constant acceleration condition. So the acceleration is increasing up to some limit, which is defined by literature. According to the comfort, it's 2.5 meter per square second. And and then cruising, and then while braking acceleration is of course negative. And the tractive force and powers is, not surprisingly, is at peak at the end of phase 1, because the drag force is highest. The velocity is already cruise, and the drag force is highest at this point. So this is the most of the tractive power that you're going to get. And the tractive power, as we see, is not fixed. It's not fixed by time. It's changing with time all the time, the tractive power. This is very important because if we consider a constant voltage systems and the power is changing, that means that the electrical current is going to change with time. And this is very, very critical for the energy loss and the design of the grid and battery system. So for the battery bank, we consider a standard lithium-ion battery as like state-of-the-art, commercial available batteries. Many companies have developed such batteries like Tesla. We must consider the operating temperature. The battery must work in order to keep a reasonable lifetime and not getting dead very quickly. One need to maintain the temperature probably below 30, maybe even close to 20 degrees. But that means that you must cool the battery. Must cool the battery. Many people ignore that. This can take a lot of energy just to cool the battery, because otherwise your battery is going to be dead very quickly. For instance, Chevrolet electric car, which is one of the best electric cars that you have, they use liquid cooling. They put cooled liquid within the plates. The plates are located in between the battery cells, and this is how they maintain the temperature. But this is, of course, costs electric energy, because in order to cool, you need some air conditioning or some compressor or something like that requires a lot of electricity, and you must account for that kind of consumption in your analysis. And our analysis resulted in a battery of 44 kilograms for a loaded car. This is the result, which is not negligible, because the whole vehicle is small, is maybe 500 kilograms, so this is not negligible. And we considered, of course, that the battery can be recharged while braking. Third rail is the other option that we analyzed. And here there is no battery, but there are other issues, like we have to supply, you have to convert AC electricity from the grid to the rail. Therefore, we need to have a power system. And there will be energy losses throughout this power system that we have to account. And those energy losses are, again, depending on the power or on the current, the electrical current that we provide to the rail, or we get from the rail while braking. So this was also taking, we also took this one under consideration. And we also accounted for the balance of plant issues. When we have a complete PRT system, it's not a complete system. It's not only about vehicles. It's also, you also have to keep stations, passenger stations. They consume electricity, and sometimes a lot of electricities. And there is vehicle auxiliaries like air conditioning, lighting, etc. And also there's the powertrain of the car. It's not just the wheel or the tractive power. There is a powertrain in the car. And here we did something that probably never was carried out before, which is to model the grid and the battery, which means we don't use a simple single value for the efficiency for the grid or the battery, but we model it according to the current or the power. As I mentioned before, it is much more accurate and much more realistic, because this is what's happening actually in a real system. Okay, and just to complete the data, because we were opting for techno-economic model, we have to consider some economic values. So we have to pay for the electricity coming from the grid, unfortunately, but and we have to install the battery and the charging stations together with the grid connection. Battery, by the way, is not just the battery, it's the entire battery management system, as they call it, BMS, and the cooling system and the power power engineering that is involved with the battery system. Everything has to be accounted for. And in the third rail solution or alternative, we don't have a battery, but we have to electrify the rails, which can be very expensive. Unfortunately, we don't have data. We don't have data for third rail, which is suitable for small PRT vehicles. So we use a value which is available for large trains, we think that it might be not so accurate, okay? But we don't have anything else, so we use this value, which can be too much oversized, like for the PRT, probably the electrification, because the PRT is a small vehicle, is based on small vehicles, it could be much cheaper actually, but we don't have a reference value, so we don't consider them. Okay, and grid connection also for the third grade, of course. So the results, the bottom line is we try to compare the energy consumption of the several alternatives. So we have two alternatives in our work, battery PRT or third rail PRT. And we have a reference PRT data because commercial PRT, there are few commercial demonstrations already for PRT, so we could compare to. But we can also compare to other transport alternatives which are not PRT at all, like tram or metro or public buses or private electric cars and so forth. So the results, and we measure the results by the kilowatt hours per passengers per kilometer. Okay, so that's normalized energy consumption. How much it costs to take one passengers, how much energy it requires to take one passenger 1 kilometer. This is very common measure. And we see that the battery is the best. Third rail is not bad at all. And the PRT as a whole is much better than any other transport option that we know about. For instance, private electric car is consumes much more energy than PRT, which is very remarkable. A result, which means that PRT in terms of energy is very efficient. And the cost, we got the cost of the battery option is much lower compared to third rail because, again, I think it's because the third rail electrification data that we used is based on the large trains and not PRT. So that might be the reason, and we can extend the work further if we refine the models to better model the powertrain and the battery thermal management, which is a big thing in batteries, and also include the issues that were not taken into consideration here, infrastructure costs and environmental impacts. So the bottom line is that the energy consumption is relatively low. The cost is very attractive, but maybe the most important thing maybe about PRT is that if we had PRT in Tel Aviv, actually, my students will no longer have the excuse why to come late to the class. So that's maybe the most important thing about PRT. So thank you, and I'm open to any question.
Thank you, Gur. Gur, we have one question from Nadav. He's asking about the concept. Is it a real project or only?
Right now, it's only a study. It's only a study, but but maybe Professor Ariel Avineri can extend on this. But it's a study. But in order to push the decision makers towards installing real plants, we need to convince them first that it is cost effective and energy efficient, etc., and practical and so forth. So this is like we must do a study before we can convince anyone to make a decision. But I believe Professor Avineri is more educated about this issue of implementing PRT.
Okay, and Ariel, you want to say something? Yeah, Ariel.
Just to say it's not completely theoretical. There are few systems that are operated on a mini scales around the world. One system is operated in Heathrow in London, another one in Masdar City in India. So there are a few examples of how this can be actually be implemented. Our model was using the most updated data. So it's kind of the next generation of PRT rather than the systems that are already been activated. Also, I see that Nadav asked whether it has some advances over the concept of light rail. So these are two completely different concepts, as this system is not supposed to transfer a large amount of people at the same time. It's more a concept that is competing the personal car rather than the light train or metro, as it's supposed to give high level of service and not sharing your ride with a large number of individuals like in the bus or in the light rail. So it cannot be compared at all, not by its function and not by its energy consumption.
What about I think that I heard about Elon Musk talking about something like this, but underground with electrical vehicle, of course, Tesla electrical vehicle.
The Hyperloop concept is then again another completely different concept. It's about transferring people over very large distances. It's not relevant to the urban movement. It's more like interurban of many hundreds of kilometers. It won't be efficient, probably won't be efficient for the distances that are common for urban travel.
Yeah, I can see Dvir is asking about the range. There is a range in the kilowatt hour per passes per numbers. What is the impact in, is it so much?
Yeah, per passenger, it's the difference is due to the fact that there are different designs. Each system, each commercial system has a different design, different vehicle size, different kind of batteries, different kind of grid power system. I mean, it's the designs and the layouts are different. So you can get a range of energy consumption in such kind of analysis. We did too. We just did not present here in this presentation the sensitivity analysis that we carried out. We did not present it, but we did it ourselves. So there is in any energy management analysis, you will have some kind of uncertainty because your input data is not certain.
So I think we are a little bit behind schedule. So if you can answer through the chat, there were some questions. I think we didn't speak about the, the environmental impact, putting such a big thing, in the city. Outside, there's a lot of impact, a visual impact I'm talking about. Yeah, we didn't speak about it.